All right, let's get right into it. Welcome, focused learners, to this explainer. If you're gearing up for the upcoming CBSE Class 10 Science Board exam, well, you're in exactly the right place. Today, we're going to completely demystify one of the most notoriously tricky sections of the entire syllabus, the electricity chapter. Now, before we start, I gotta check your Josh meter. Are your energy levels high? Because we aren't just going to study today, we're going to strategize. We're going to look at the exact traps those examiners set, the core concepts you absolutely have to master, and the foolproof algorithms to lock in literally every single mark. So let's get that Josh meter fully charged and dive right in.
Okay, let's start with a really painful reality. Are silly mistakes completely wrecking your physics score? Time and time again, I see these brilliant students, students who understand the theory perfectly. They walk out of the exam hall, check their answers, and suddenly realize they've dropped 5 or 6 easy marks. And why? Well, it's rarely because they didn't know the physics. It's almost always because of these tiny, frustrating errors in their numericals. You see, the board exam is designed to test not just your knowledge, but your attention to detail when you're under pressure.
Okay, let's dive into this. Here are the absolute biggest traps that examiners use to catch you off guard. First up, unit conversions. They love to give you current in milliamps, and if you plug that directly into your formula without converting it to amperes first, your entire calculation is doomed right from step 1. Second, the parallel resistance trap. You do all the hard math, calculating 1 over R1 plus 1 over R2, you get a fraction, and you stop. But wait, did you flip it to get the final equivalent resistance? Most people just forget. Third, we've got sign conventions. Placing an ammeter or voltmeter with the wrong plus-minus polarities in a diagram will instantly lose you marks. And finally, the ultimate tragedy, doing the whole problem perfectly but forgetting to write ohms or volts at the end of your answer. Just brutal.
So, to avoid falling into those traps, we really need a rock-solid foundation. Welcome to Boss Level 1, Visualizing Resistance. Whenever you're faced with a complex network of resistors, the ones with all the branches and multiple paths, your very first step should never be picking up your calculator. Seriously, put it down. Your first step is to use the circuit diagram as a sanity check. Literally take your pencil and trace the path of the current. Where does it split? Where does it come back together? Actually visualizing the layout tells you exactly which components are in series and which are in parallel before you crunch a single number. Now that we know how to map out the battlefield, we have to understand the fundamental boss of the chapter. Enter Ohm's law. This is the core linear relationship that dictates exactly how electrical circuits behave. It simply states that the potential difference, meaning the voltage, across a conductor is directly proportional to the current flowing through it, provided the temperature remains constant. Think of voltage as the pressure pushing water through a pipe, and current as the water itself. The harder you push, the more water flows. That simple, beautiful relationship is basically the beating heart of this entire chapter.
And here is exactly how we translate that concept into our ultimate weapon. V equals IR. Voltage equals current multiplied by resistance. I honestly cannot overstate how absolutely crucial this formula is. It is the master key for leveling up your numerical problem solving. Whether you're trying to calculate the total current drawn from a massive battery or just finding the potential difference across one tiny little resistor in a huge circuit, V equals IR is the tool you're going to reach for like 90% of the time. Burn it into your memory right now.
Now, what's really interesting about this slide is how examiners love to test this concept visually using VI graphs. When you plot voltage on the x-axis and current on the y-axis, or vice versa, a material that actually obeys Ohm's law will always yield a perfectly straight line passing right through the origin. But here's the catch. If that line starts to curve, it means the resistance is changing, maybe because the wire is heating up, and boom, it's no longer following Ohm's law. Plus, the slope of this line actually tells you the resistance. It's just a brilliant way for them to test your conceptual understanding without making you do heavy math.
All right, let's pull this out of the textbook and into the real world for a quick showdown. Parallel versus series circuits in your actual house. We wire our homes in parallel. Why? Because it guarantees that every single appliance gets the exact same voltage. It also ensures independent operation. Think about it. If your bedroom light bulb burns out, your refrigerator in the kitchen doesn't just suddenly shut down, right? But in a series circuit, the voltage gets divided up, so things wouldn't even run properly. Worse, dependent operation means if one single device fails, the whole circuit breaks. Kind of like those cheap holiday string lights. It's wildly inefficient and completely unsafe for homes.
Speaking of appliances, there is a magic number you absolutely must memorize for the exam: 220 to 240 volts.
This is the standard alternating current, or AC voltage, that gets delivered to Indian domestic circuits by the power stations. When you're calculating the power or the current drawn by a household appliance, like a TV or an AC unit in your numericals, this is the standard voltage value you're going to use if they don't explicitly give you one in the question. Definitely keep that number handy.
Okay, we've officially reached boss level 2, Joule's law of heating. See, electricity doesn't just flow around, it does actual work, and sometimes that work involves battling against resistance, which generates heat. But here's the cool part. This isn't just a byproduct, it's something we intentionally harness. Like for breakfast. Think about an electric toaster. It purposefully uses high-resistance wires to generate enough heat to crisp your bread. Traditional filament bulbs glow that bright yellow specifically because the filament gets so incredibly hot from its resistance. And electric fuses? They are literally designed to melt and break the circuit if the current gets dangerously high. We're using that heating effect to protect your expensive appliances from totally frying.
But hey, fuses aren't our only line of defense. Safety in domestic circuits is a massive topic for the boards, which brings us to earthing. Earthing is this brilliant safety measure that uses that thick green wire you've probably seen inside heavy cables. It provides a dedicated, extremely low-resistance path for leakage current to flow safely directly into the ground. So if an appliance with a metallic body, say your washing machine, has a fault and the live wire touches the metal casing, that earth wire acts as a shield. Instead of that current traveling through you and giving you a severe, potentially fatal shock, it just takes the easy path right down into the earth.
Knowing how circuits work in our walls is great and all, but now it's time for boss level 3. And this brilliantly illustrates what we're up against, mastering the dreaded circuit numericals. You are absolutely going to see complex diagrams like this on your exam paper. A battery, maybe a key, an ammeter, and a whole messy combination of resistors in parallel and series. I know, it looks super intimidating, right? But remember what we talked about at the beginning? It's not about being some natural math genius, it's about being structured, organized, and not falling for traps. To conquer a complex setup like this, you just need a system. And here is that system, the foolproof algorithm to completely outsmart the examiners. Step 1. Standardize. Scan the question and immediately convert every single value to proper SI units. Step 2. Draw. Actually, even if the question doesn't specifically ask for it, sketch a quick rough circuit diagram. It genuinely helps your brain map out the problem. Step 3. Calculate systematically. Always start with the innermost parallel branches. And please, remember to take the reciprocal to find the actual resistance. And step 4. Show every single step. The CBSE board awards stepwise marks. Even if your final math at the very end is a total disaster, if you wrote down Ohm's law and substituted the initial values correctly, the examiner literally has to give you marks. Make them give you those marks.
So, the crucial point is this golden rule, and you must never break it. Never leave a numerical answer without its unit. I'm repeating it because it is, without a doubt, the most heartbreaking way to lose a perfect score. You can do all the complex fractional math, apply Joule's heating formulas flawlessly, and find the exact equivalent resistance. But if you just write 5 instead of 5 ohms, or 10 instead of 10 volts, the examiner will deduct points. Just put a big, bold box around your final answer and make absolutely sure the unit is sitting proudly right next to it. All right, let's wrap this up with a little puzzle for you to chew on, a thought-provoking scenario. If you double the diameter of a wire, what happens to its resistance? Think about it. Remember the formula for resistance involving resistivity, length, and area? Remember that the diameter affects the area, and area squares the radius. So, does the resistance simply drop by half, or does it plummet all the way to 1/4? I'm going to leave you to crunch those numbers. Mastering these conceptual leaps without constantly having to reach for a calculator is exactly what separates a good student from a topper. Keep mapping those circuits, watch out for those sneaky unit traps, and go crush that exam.